Hi, my name is Jan Jungboom, and in this tutorial we'll be building a computer vision system that can recognize two different types of objects and it then runs on a microcontroller in real time. Now, if you want to build a system that can recognize two different types of objects, then, well, we need two types of objects. Here I'm going to be using two things that hopefully everyone has in their home, which is a plant and a lamp. So on my left, I'll put a picture here, I have a plant. And here on my right, I have a lamp. Now, when I want to train a machine learning model that can distinguish between these two types of objects, first of all, I need to start building a data set. So I need a kind of a wide variety of pictures of both the plant and the lamp. And these need to be different in orientation, in angle that they're being shot at, and the crop that we make of them. So to make sure that the model works well, it actually renders on device later on. So we kind of need about 30 photos of the plant, we need about 30 photos of the lamp, plus an additional maybe 50 photos of things that are neither a lamp nor a plant, because otherwise the machine learning model won't generalize well, and when I make a photo of my screen, there's no way in a neural network to say, well, this is neither of these two things. So we need to give lots of examples there as well. Now you might think that, well, 30 plus 30 plus 50 is 110 photos. Isn't that very little for kind of a computer vision model? I thought these things need lots and lots of data. That is typically very true, yes, but what we've added in Edge Impulse is transfer learning, which allows us to train a very generic machine learning model, strip off some of the layers of the network, and then retrain that with your data. And this allows us to get really good results, even on very little data, like the 110 images that we're going to collect here. Now, how do we get these? How do we get this data? Well, the easiest, if you already have a data set, or you want to make photos with your phone, or anything like that, is the uploader. So you head to data acquisition, you had the little button here, and from here you can just select your current data set, split it in a training and a testing set, and then give a label. The easy way to get started if you already have a data set. Alternatively, if you have a device that supports direct sampling from the camera, or if you have a mobile phone, you can get data straight from the record new data widget. So if your device shows up here, you'll have a camera sensor, and here you can say, well, I want to make a photo of the lamp, and here I'm using my phone, and I grab a capture. And there we go, that is the first item in my data set. Easy. Alternatively, and this is relevant for the current tutorial because we are going to run this system in the end on this development board, is that you can also use the OpenMV camera to do this. So this is a really beautiful small development board. It supports a Cortex M7 microcontroller running at 480 megahertz and this beautiful camera module. Now the OpenMV camera comes with its own IDE, the OpenMV IDE, which has really great additional tools to do this kind of data set capture. So I can go into the OpenMV IDE, say, well, I want to create a new data set. In our case, this will be plants versus lamps 3. I open it, and from here I can add new folders. So I say, well, I want to have a plants folder. I want to have a lamps folder and an unknown folder. So this gives me 3. Here I want to set my windowing to a square frame because the transfer learning model that we're going to be using uses square input images. So by capturing this stuff already in a square frame, this means that we don't have to squish the image down later. And I connect to my dev board and then run this script. So after that, you'll see that indeed on my left, I have a plant, and on my right, I have a lamp. So to capture a photo now, all I need to do is I click on the plants icon, I snap the photo, and now I have something added to my data set. I do this similarly for the lamps data set. As said, it's really crucial that you capture a whole wide variety of things. And then a bunch of things of the unknown class, like my keyboard, the floor, or the ceiling here. Now, once you've collected these kind of 110 images, you can then either upload this data through the UI. There's a bit of clicking and you need to input the categories, or we can use the Edge Impulse CLI to upload this data. So the Edge Impulse CLI is a local program that you install. You can just call the uploader with format OpenMV and then the location of your data set. Now this is non-destructive, so you can run this multiple times. Also, if you're adding new data to this data set, you don't need to remove the data from Edge Impulse first, because we do a duplicate check here. So here I have my 111 files, and now when I go back to the data acquisition page, now I have a pretty nicely balanced data set consisting of 83 items in my training set. So we automatically split the 110 files between a training set and a testing set for data sanity. 83 items split between unknown, plant, and lamp. And we also have a variety of items, in this case 29 items in our test set. Now how do we go from all these images? There's some random stuff on my floor, this is my living room, and this is a plant. How can we distinguish between these two things? Well, for that we need to start building a machine learning pipeline. So we do that by going to the Create Impulse screen. As you can see, we have image data here, and the first step that we need to do is resize all of our images. It's really crucial that they're all the same size. My data set might actually consist of images both captured on the OpenMV cam, images from an external data set, and images from my phone. So this is the very first sanity check. If you want to use the transfer learning blocks, which I'd recommend for vision models, then it's recommended to set this image size to 96 by 96, because that's what the transfer learning model was being trained on. Now the second thing is that we want to add a processing block. So processing blocks take input data and then spit features out. So what we do for image data is that we can reduce the color depth. So if we don't think that RGB color is necessary, we can turn our images into grayscale and use those features instead, which means you have kind of 3 times as little information, and thus your model requires 3 times as little space to run on the device in the end. But you can also but through our custom blocks feature, you can also add custom processing blocks. Maybe you want to add some pre-processing to these files, maybe you want to do something with infrared images. This is all stuff that you can do through these processing blocks. All the sources available, so you can modify it. Here we'll go with the standard one, and then we'll add a learning block. And the new thing here is our transfer learning for images block. So here we have a pre-trained image model, where we strip off a few layers, and then we retrain those layers with your images. And why is that? So why does that actually work? Well, the magic here is that computer vision models on kind of the lower layers of the neural network all need to learn the same features. They need to learn about contrast. They need to learn about shapes, about images, about color in general. And these will often be the same regardless of your data class, as long as you're doing stuff with photos and things in the real world. However, if you have very little data, it's very hard to train a model like that. Because if we only have 110 images, there's probably ways for the model to take shortcuts and does not learn that a plant is green and has leaves, but rather than there is something that distinguishes the plant from the lamp. Here probably maybe there's a bit of white background because the placing of these things is different or the lighting conditions are different. By using a transfer learning model, we first force the model to learn generic features because we train this on much wider data sets. And this is great because afterwards the model will be much more resilient when feeding data in that's just a little bit different, but still has leaves and is standing here in my living room. So this is pretty great. So not only does it make training a lot shorter, you actually go from days of training on a GPU to being able to train this model in a few minutes. It will also generalize a lot better on small data sets. So let's add this and save our impulse. So on the image screen, I first have my image here on the top. My raw features are the RGB color codes per pixel that I have. And then it's my DSP result. So I can change the color depth to grayscale if wanted and look at some of the other data in my data set. So I'll see plant here, other plant. For now, we'll use an RGB data set. So I'll save my parameters and then click the Generate Features button. What we do here is that we go over all the data in the training set, resize this data to the 96 by 96 pixels, run it through our pre-processing block, extracting some features. In our case, on a you have 3 features per pixel, an R and a G and a B feature. And then we run a dimensionality reduction algorithm, UMAP, over this data. So we have a visualization of our data set that we can compare. So we don't have a lot of data here, so our feature explorer looks a bit sparse. But what is cool here is that you can actually see some clusters appearing already. So we see that there's a cluster of lamp data here. There's a cluster of plant data sitting here, and there's some stuff here in the middle, and we see some unknown data as well. This is kind of cool. If you see that your data set starts separating here very well, that means you're doing something, that means your data is kind of different enough already. If you see that lots of stuff is really clustered together, it might be that you have issues with your data sanity. It could be that data is mislabeled, for example. Now, if you guess that, you can just click on one of these items and the picture will show up here. And by clicking on these things, you'll see that actually our dimensionality reduction algorithm has found a bunch of pictures that look alike. These are all kind of from the same angle, and it's clustered those in the same area. Similarly, if I click here on the plant data, these are all almost like a different crop of the same image. So this is pretty cool, especially in a larger data set. This is super useful in finding kind of anomalies in your data set and finding things that are mislabeled. So with this all ready, let's go to our transfer learning option. We have a number of transfer learning models that we can run from here. And that depends a bit on the size that you can run on your device and your requirements. So we have a MobileNet v2 trained model here that is trained on a set of color images. If I rather have one that works on grayscale images, I can do that as well. And you can see here that the color image one, at least the one that we select here, is about 687K in size. This is the size of the network after quantization and TensorFlow Lite. And the grayscale one is only 270K. And we'll be adding even smaller models in the future to make sure that these run on all microcontrollers. But actually for the OpenMV camera, with its Cortex-M7, we can actually run the color model without any problems. So let's set the training cycle, so the number of time, you can kind of see a neural network as a really large mathematical formula, and all these, in this formula there's lots of variables, and we try to like adjust those while we're training. And the number of training cycles here we set to 20, because we do this 20 times for the whole data set. We can set our learning rate. And then last, something new as well, is that we can set our data augmentation. So when we do that, then during training, we randomly flip images, make crops of images, tilt them a little bit, to make sure that we kind of create some artificial data. So if you forgot to include certain parts, certain like orientations on the plant, we try to do a little bit better on real world data. And then we set our minimum confidence rating to about 70% to help us with validating how well our model works. So this will now strip off some of the layers of the base neural network, and then retrain that, and you'll see the accuracy and stuff going up. And even for a model, for a vision model, which is traditionally very hard to train and take a very long time, this will end pretty quickly. So after the initial 20, we'll still be a bit of fine-tuning on the best model that we found to improve performance. So now model training is complete, and we see at the bottom here our training performance. So we achieve very good accuracy, actually, here 94%. But this is only on a very, very, very small cross-validation set. So don't think too much about it. We'll see a confusion matrix as well, very useful if you have lots of data. But most interesting is that we can actually see the on-device performance. And this is actually measured on the OpenMV camera, so a Cortex-M7 microcontroller. So we see about peak memory usage of about 450K and an inferencing time of about 370 milliseconds. Very, very decent on an embedded system. And this can even go faster if you run this on, for example, an embedded Linux system, or if you choose a smaller model. But good enough to do stuff in real time. Now, as said, we can't really trust this number, but rather we want to use the data in our testing set when we did the data collection earlier, we split our data automatically between the training set and the testing set to do the validation. So let's take a look at how well it does there. So I select all my data, I select classify, and I will do the same thing as we did earlier during training, but now in our testing set. We look at all the data, we resize it, go through a pre-processing step if needed, and then classify against our transfer learning model. So there we go. Actually, on our testing set, an accuracy of 89.66%, which is really good, actually. Naturally, the interesting bit is where did the model get it wrong? So we can go through all of these samples, all of these are in our testing set, and click on the three dots and then click Show Classification to go into more detail on what was happening for this specific image. So here we see actually it was pretty sure that it was unknown, but only 68%, so not that interesting. Let's look at 0017, see if something else is going on. So here uncertainty is not that bad. Actually, pretty successful here, 89% on just such a small image set. Now, if you have a device that supports live classification, like a development board with a camera on board that runs that is fully supported by Edge Impulse, or if you have your phone on you, you can also use your phone to do live classification here. So let's say let's do the lamp again. I click Start Sampling. And from my phone, I make a picture of the lamp. It now uploads this to Edge Impulse and then goes through the same classification pipeline. So it doesn't run on device yet, but as said here, indeed, it thought it was a lamp 100% of the time. So pretty great. That is something that we were kind of expecting. Great. We have a model that actually works. We validated that the model works on real life data. We've checked with our live classification view that even on a completely different device than where we collected the data, our phone, the model still performs great. So now deploy it. Here's a variety of options. So if you have an embedded device already, you can just export as a C++ library. We then get all the dependencies, all the pre-processing code, all your neural networks and all the code to do the inferencing. Wrap it in a single C++ library without any external dependencies, but also including a bunch of hardware optimizations if your device supports it. So on Cortex-M class devices, we can leverage the vector extensions in silicon to actually make this run really, really fast, and actually do this in real time on these devices. And that's interesting because we're going to run this on the OpenMV camera, I can now export as an OpenMV library. And when I build, I get a zip file. And in that zip file are three files. There's the labels file and a train.tf-lite file. And then the final script that I want to run on my device. So let's go back to the OpenIDE, stop the current program, and then drag the labels.txt file and the train.tf-lite file to no name, which is the name of the USB flash drive that mounts when you connect the OpenMV camera to your computer. So this is overriding, loading the trained machine learning model here. And then I can go back and I can select the EI image classification view, open it with the OpenMV IDE. And this is a script that is already adjusted to use the ML model that we just created. So let me open the serial terminal here so we have a bit of an overview. And click the play button to flash the script. So this is now running on device. Well, as you can see, we have a little view here of the frame buffer on the right. This is running embedded in real time. It's about 2.5 frames per second, which part of it is still actually being used for writing to the frame buffer. And at this point, we see that we are unknown. Now the interesting part naturally happens when I start moving this thing around. So let me actually point it to my lamp. So 91% sure that this is a lamp. Super cool. When I move it around again, this jumps to unknown, which is totally what we want. And then when you ship to the plant, we see that indeed we're very, very sure that this is a plant. So this is a model that with just 110 images, actually works good enough to run in real time here on a microcontroller, which is absolutely fantastic. So yeah, this all is mind-blowing to me. The fact that we can actually train a machine learning model with just a little over 100 images and then perform well in real-world scenarios. Like, this is hard. We're in a living room with lots of different objects. And even being able to do this in real time on a microcontroller. This is just a microcontroller with a Cortex-M7 on it. Is absolutely mind-blowing to me. So if you feel inspired and you want to go do this as well, head to Edge Impulse, sign up, grab either the OpenMV camera or your mobile phone or a dataset that you already have, and start building. Computer vision is a super interesting field. It has some amazing applications in industrial space, in safekeeping, or even something we're doing currently with a customer in wildlife preservation. Okay, you detect if you see a poacher where there shouldn't be one. This is all stuff that you can actually start building and actually deploy on small battery-powered devices. So with that, thank you for watching, and we can't wait to see what you build.